So, yesterday we were discussing about orthogonal polynomials. Okay, so is board visible? Okay.
Yeah.
Yeah. So, yesterday we said that there is an interval a to b and there is a weight function rho of x. Then we can discuss about the orthogonality relation between the polynomials phi n of x and its completeness relation, right? So that's what we did yesterday. And so now the question is, suppose I define rho of x and I define the interval. Does it uniquely determine the polynomial phi n of x? Okay, the answer is yes. So if I define rho of x and if I define the interval, I can actually uniquely find out this phi n of x. So how that test can be done? So let me just, because I am not, because the proof of this is very long and I will not be presenting the proof. Right now you just take the answer. So whoever is.
So uniquely defined means only one polynomial exists.
Yes. Yes. And
for this particular function.
For the particular function rho of x and the domain AB, interval AB. Okay, so that is important. Yes. So if you have, I think most of you have the Balakrishna's book, right?
Yes, sir.
Yeah, so you, the more details regarding this special functions and all, you can actually refer to the books given in that Balakrishna's reference. Okay, so when you refer this part of the in Balakrishna's book, it will actually refer those books important regarding special functions, orthogonal polynomials and all. So right now what I am going to do is I will teach certain things which is actually you require to do the further courses in the department, okay, because that is very crucial. So I will not be getting to the deep of the orthogonal polynomials and the, these special functions. So I will teach whatever is required so that you can actually, when you face the quantum mechanics or any other physics subjects later on, you will not face difficulty. So that is the idea. But the special functions itself can be one full course. Okay, so we are only taking whatever necessary and sufficient for your further study of other courses in the department. Okay, so I have a weight function rho of x and there is a limit AB. Okay, the interval AB. So obviously the phi 0 of x. Yeah, so uniquely when I say phi 0 of x you have to fix, right? So phi 0 of x you take some constant C0, okay, because this is a polynomial of order 0. So when you take phi 0 of x is equal to C0, now I can define or I can find the moments with respect to rho of x, x raised to k. So I define this as mk, okay. So I define this as mk, let me use this notation, okay. So this is kth moment of x, okay, with respect to the weight function rho of x. So this, suppose this is defined, okay, you can define this, there is no problem, okay. Now how do I find out all phi n of x? That is the question, okay. So the phi n of x is basically equal to an n plus 1 determinant, okay. So you write down x square up to xn. So this is phi n of x is equal to then m0 m1 up to mn minus 1. Okay. Here m1 m2, what will be this one? Mn. So this will be Mn, and what will be this one? M2n minus 1. Okay. So the phi n of x is equal to the determinant of this matrix or the determinant of this quantity. Okay. So what is the dimension of this matrix? What is the dimension of this matrix?
n by n.
Is it
n plus 1.
n plus 1 by n plus 1. Okay. So I can uniquely define phi n of x, okay, from this, okay, if I know rho of x and the interval a b. Only thing is I have to calculate this quantity. So there are various ways to find out phi 0 of x. Okay, this is the one way of getting the answer. So we will be learning, okay, what are the different ways to calculate this phi n of x for a given interval and for a given weight function. Okay, so that is our, but the uniqueness is basically this: given rho of x and a b, my phi n of x are fixed, provided phi 0 of x is equal to c 0. So now let us look at the hypergeometric differential equation. So what is a hypergeometric differential equation? It is basically a second order differential equation with a sigma of x d square phi by dx square plus tau of x d phi by dx plus lambda phi equal to 0. Okay. So where sigma of x, tau x and lambda are polynomials. So sigma of x is a polynomial of order 2 and tau of x is a polynomial of order 1 and lambda is a constant polynomial of order 0. So sigma of x, you can write it as sigma 2 x square plus sigma 1 x plus sigma 0, and tau of x you can write as tau 1 x plus tau 2, and lambda is constant. So this is basically the hypergeometric differential equation. Now when can you get an orthogonal? Yes.
What is phi here? Orthogonal polynomial?
No, so no. That's what I am saying. So we are not into that. So what is the statement I made earlier is, so we actually seen given the weight function and the interval, you can actually uniquely determine phi n of x, those orthogonal polynomials. Now I have a hypergeometric differential equation. That is this. Here this phi is any function. Okay. So when can you get orthogonal polynomial as a solution to this? So phi become phi n of x. What is the condition for that? Okay. So that we have to now give. Okay. So in general the solution to this is not a orthogonal polynomials, but under certain conditions the solution to this will become orthogonal polynomials. So what is that condition? So that condition is basically something relating between sigma, tau and lambda. If there is some relation between these three functions, so this is a or 3 polynomials, then we can get an orthogonal polynomials as a solution. So what is the condition? The condition is this: sigma lambda n is equal to minus n into n minus 1 sigma 2 plus n tau 1, okay, where n is equal to 1, 0, 1, 2, etc. So you have the hypergeometric differential equation and this coefficient or the polynomials which are the coefficients of this differential equation, if they satisfy, so that means lambda n means, okay, for some particular value of lambda, okay, if that is equal to minus n into n minus 1 sigma 2 plus n lambda 1, where n is equal to 0, 1, 2. So sigma 2 is the coefficient of x square in sigma of x, and tau 1 is coefficient of x in tau of x. If they satisfy like this, so if this coefficient is equal to n into n minus 1 of sigma 2, okay, plus n into tau 1, then you get solution to this as orthogonal polynomials. Okay, then solution to this differential equation will be orthogonal polynomial. Okay. Yeah.
Sir, for different values of n, it will be different set of solutions.
See that obviously, see your phi n of x, you have n 0, 1, 2, 3, infinity, right? You have so many. So what is phi 0? So phi 0 means you put n is equal to 0. Okay. So put n is equal to 0. See what is the, so what lambda sigma 2 lambda, see if that is this equation is satisfied, you get phi 0 of x. Now put n is equal to 1. If this equation is satisfied, you get phi 1 of x. So these things will have that solutions. Okay. Okay. So there are infinite number of solutions for this. Okay. For certain sigma of x, lambda of x, and lambda. Okay.
Sir,
Yeah.
sigma and tau can be of higher power of x or this much only?
So this one, see, we are talking about hypergeometric differential equations. The hypergeometric differential equations, the power of sigma of x is this, second order. Okay. And tau of x is first order. So we are not only talking about that. Okay.
Yes, sir.
Okay.
And sir, this sigma of x and tau of x remains same for a same set of, like, it won't change, isn't it?
See, if for one set of things, obviously it should not change because here you see different lambda. So you change lambda, you get different phi n of x. Sigma 2 and tau 1 is fixed. See? Okay. So now this is called the solution to this hypergeometric differential equation when this see here now I am only talking about real solutions. Okay. I am talking about real functions. So this can be analytically continued to complex space. Okay, so I am not discussing that. So right now we are interested only in the real polynomials. Okay, so this x can be easily replaced with the z, the complex number. Okay, is the board visible? Okay, light has come. So for this hypergeometric differential equation, if this condition is satisfied, you get phi n of x, they are orthogonal polynomials. Now, what is a classical orthogonal polynomials? So there is an additional condition. Okay, so what I said was, if this, for this differential equation, if this condition is satisfied, we get phi n of x, which are orthogonal polynomials. So what is a classical orthogonal polynomial? The classical orthogonal polynomial is if sigma of x into rho of x So sigma of x is the coefficient of the second order differential function d square phi by dx square, okay, second order differential. So sigma of x into rho of x is the weight function at x is equal to a and x is equal to b if that is equal to 0, okay. Then we get classical okay. So if additionally to that, if this condition is also satisfied, then we get classical, so additional thing, classical orthogonal polynomials. So there are three types of classical orthogonal polynomials, 3 times 3 classes, okay. So what are they? That depends on so there are 3 intervals you can think about, right? So what are the 3 basic intervals? What are the 3 basic intervals?
Minus infinity to infinity.
Mm-hmm.
A to B and 0 to infinity.
Mm-hmm.
And a to b.
Okay. So one is minus infinity, infinity. Other one is 0, infinity. Then minus 1 to 1. Any other interval. So this is infinite, right? This is semi-infinite and this is finite. So any finite interval you can scale to minus 1 to 1. Okay? And this is infinite interval, this is semi-infinite and this is finite. So there are 3 different types of intervals. Corresponding to that, whatever the conditions I said earlier, if those conditions are satisfied for the hypergeometric differential equation, I get 3 classes of polynomials. So this class is Hermite polynomial. This is generalized Laguerre polynomials. This is Jacobi polynomials. So all these polynomials are very important in physics, okay, because you come across, you must have already, the BTech students must have already came across some Jacobi polynomials when you have done the electrodynamics, right? And there are so many other instances you come across all these polynomials. So for the infinite, Hermite polynomial, and semi-infinite generalized Laguerre polynomials, and finite interval is called Jacobi polynomial. So there are 3 classes of classical orthogonal polynomials depending on this interval, and they are basically the solution of hypergeometric differential equation which actually have certain conditions satisfied, okay. Now, so already we said that how do we get those polynomials, right? So one method is to find out the determinant of that matrix, okay, after finding the mk values. So there are different other ways to find out these polynomials. One is actually using the first let me say the Rodrigues formula, okay. So what is the Rodrigues formula? So phi n of x is equal to kn divided by sigma rho of x, then dn dx, nth derivative of sigma power nx okay. So you know what is rho of x, that is basically the weight function. Sigma is basically the coefficient of d square phi by dx square in that equation. So this kn are n dependent constants. So I can calculate phi n of x using this formula. Okay. So it's called a Rodrigues formula. So kn will be given for each type of each class we discussed earlier. Okay. So kn will be given. You can actually calculate the phi n of x for each of the three types of polynomials we just discussed. Okay. So this is called Rodrigues formula. So why we are discussing these things? Because when you do certain calculations, you may end up with this kind of differentials. Okay, because it's the n differential of some function. So then, because you know this kind of polynomials, from this you can actually easily maybe able to identify the corresponding polynomial solution for that. Okay. Other thing is you can actually generate the polynomials if I know the kn values. Okay. So there are certain cases this Rodrigues formula will help you. Okay. Or to convert from one type of differential equation to different type of differential equations. Okay, you can actually end up in this kind of Rodrigues formula so that you can find out the polynomials. So next is the generating function.
So where do we get the kn value from?
Okay, so that is basically each type of polynomial. This is actually given to you. Okay, because this is by research. Okay, it's a long. That's what I'm saying. The special functions, those books you can go and actually. Okay, so if you want kn, actually, let me just talk about the generating function. Okay, because generating function and the phi n of x, you can actually this Rodrigues formula have some relation. So or any advanced textbooks will give you directly the formula, but this can be derived for given type of polynomials, no problem. So the next is generating function. F x t. So it's a function of two variables x and t, which is equal to, it is a power series in t power n cn phi n of x. N is equal to 0 to infinity. So there is some generating function. From that generating function, I can actually calculate phi n of x. So this is basically nothing but this function you are expanding, doing a Taylor expansion around t equal to 0, right? So this function so this series is nothing but is a Taylor series of this function at t equal to 0. So what is phi n of x then? Can you just find out phi n of x from this? If I know f of x t. So this is this also the generating function for each type of polynomials we can actually calculate. So for Hermite polynomial or Jacobi or Jacobi or class of polynomials, there are so many polynomials into that. So each of those polynomial actually there is corresponding generating function. So if I know the generating function, I can easily calculate phi n of x. Okay, but also other places this formula will help you. So anyway, there are so many assignments we can do so that you will understand the usefulness of these generating functions. So from this, what is phi n of x is equal to? What is phi n of x is equal to? Can you give me? So you are saying phi n of x is equal to,
and the derivative of f but with respect to t
okay,
at t is equal to 0.
is that is it?
This reflected by 1 by Cn.
Is it correct?
Sir, there will be a n factorial.
There will be,
Factorial of n factorial.
I think somebody already said this answer initially, right? Yeah. So this is basically phi n of x. So if I know the generating function, I can calculate phi n of x. Okay, so now you have three methods. One is Rodrigues formula, second is generating function. First one is whatever I said, that matrix in which is contains the m, the moment of s power x. Okay. Now let us look at the next one. Next is the orthogonality relation, right? If I have the orthogonality relation, that is if I know this, is it possible to find out phi n of x and phi n of x? Suppose I know this, is it possible to find out for all n? This is m. Yes or no? So I know rho of x, I know a n. So I will give you that. I will give you rho of x and a n. I will give you the interval also. So with this, is it possible to find out phi n of x? Okay, I will give you one more. Yeah?
Yes, sir.
How do you do that? Obviously, I should give you phi 0 of x, right? I should give you phi 0 of x. But phi 0 of x, no need to give. Why? Because phi 0 of x is a constant, right? If phi 0 of x is a C0, but the C0 I can find out. How? I can put n is equal to m, so integral a to b dx, rho of x is known, phi 0 of x square is equal to some constant, that a n is already given. So phi 0 of x I just put C0. So from that I can find out C0. Yes or no?
Yes, sir.
Yes. Now I know phi 0. Now can I find out phi 1? Yes. I know now, already I know phi 0. I got phi 0 is equal to some C0. I have this relation. Can I find out phi 1? What is phi 1? By definition. It is a polynomial of order 1. That means sum is a1 x plus a0, right? So a1x plus a0. Now you tell me, can I find out phi 1? Finding out phi 1 basically means finding out a1 and a0. So what I should do first? I
have to first calculate
so
A1.
so I have two unknowns, right? So I should have a two equations to solve. So what is the first? How do you get the first equation? You put n is equal to 1 in this. N is equal to m is equal to 1. So I get an equation a to b dx rho of x phi 1x square equal to a1 is already given. So I get one equation from that. Second equation I will get. Second equation you put n is equal to 1, m is equal to 0. If I put n is equal to 1, m is equal to 0, right hand side is 0, right? So I get one more equation. So you solve those two equations, linear equations, find out a0 and a1. Is it clear?
Yes, sir.
Yes, sir.
Okay. So from the basically this is basically the Gram-Schmidt orthogonalization. What are you doing is a Gram-Schmidt orthogonalization, because phi 0 is normalized. Now you are making phi 1 normalized to phi 0 with this normalization condition, orthogonality condition. Okay. So some other way of doing the Gram-Schmidt orthogonalization. So any orthogonal polynomial, if I know the orthogonality relation, I can find out all those polynomials. So this is the fourth way of finding out the orthogonal polynomials. So in your particular problem, we don't know where we will end up. We may get some equation like this, then we have to find out this. You may actually end up in some new kind of polynomials. Okay. So that cases no prior information, but somehow you got this orthogonality condition in your problem. Okay. So you can actually your own new set of polynomials you can derive. Okay. So we had actually some kind of polynomials we derived later, I mean some 1-2 years ago. Okay. It was completely new type of polynomials, never existed in the literature. Okay. But we have some kind of, yeah.
Can you explain again how we can find phi 1 equal confusion?
Okay, so 1 second.
Yes, sir.
Okay, so I just spent 2-3 minutes, okay, to make you to understand that. So already we found phi 0, which is something C0. Now we want to find out phi 1 of x. So this part of the things won't be available in the Balakrishna's book, okay. So this finding the polynomials using the orthogonality relation, it is not discussed in Balakrishna's book. You can look at Afghan, okay. So mathematical physics by Afghan, because there some of the polynomials they derived it explicitly. So idea is this. So phi 1 of x is the first order polynomial. So just write down that as a1x plus a2 a2. So now first thing what you should do is you take this formula. So already I know what is a0, a1, a2, a3, etc. So put n is equal to m is equal to 1 in this equation. So if you put that, what you get a to b dx. So what I am doing is n is equal to m is equal to 1. So dx rho of x phi 1 of x square, okay, because n is equal to m is equal to 1 equal to a1. a1 is known. Now if you substitute this, basically what you have to do, the square of this you have to substitute in this, and so you basically what are you going to get if you substitute a square of that? a2 square plus a1 square x square plus a1 a2 x. Okay. So you substitute that in this, then what will happen is this integral you can actually do the integration, right? You will be able to do this integration because it's just a polynomial and a to b and rho of x. Okay, so you perform the integrations, but the integration result will be in terms of a1 and a2. Yes or no?
Yes, sir.
Yes, integration result is in terms of a1 and a2. Now what next you have to do? Next you put n is equal to 1 or n is equal to 0 and m is equal to 1. If you do that, what are you going to get? You get a to b dx rho of x phi 0 of x phi 1 of x, which is equal to 0, right? Phi 0 of x, phi 1 of x is equal to 0. Now you substitute phi 1 of x is equal to a1x plus a2 here. Then phi 0 of x is already known, you substitute that, right? So this left hand side, what do you get? You get an answer in terms of a1 and a2. So something you get a1 into some constant, okay, so you call it as constant as b1 plus some b2 a2 equal to 0 you get, right? From this equation what you can understand? You can get a relation between a1 and a2, right? Because a1 and a2 are related because right hand side is 0. So you can now write down a1 in terms of a2. Now if you write a1 in terms of a2, this equation is very simplified. So first you do this integration, then you come back to this. So from this equation you get a relation between a1 and a2, that a1 you substitute here, then you do this integration. So this integration will be left hand side, you will have a some a1 into some answer which is equal to something. So you find out a1 or a2 to something which is equal to something. So you find out a2 or a1 from this equation. So you solved a1 and a2. Is it clear?
Yes, sir.
Yeah. So what you can do is I will discuss certain polynomials now. First I will discuss the Hermite polynomial. So when I do the Hermite polynomial, you will understand what is rho of x, all these details you can get it. After that you can try to solve phi 0, phi 1, phi 2, at least first 2-3 polynomials using this. Okay. So one is what you are going to get is you get certain equations, that equations you can solve using this orthogonality relation, then you can find the polynomials. So any questions whatever you have done so far today? I will stop here. Yeah.
Phi 0, phi 1, phi 2 that we are taking as C naught or A1x plus A naught, these are assumptions, right? We are assuming phi ends to be of the order like the power of x to the power n, like summation.
Yeah, see, by definition, see, that's what we started with saying that phi n of x. Okay. So we are not assuming it. It is that. Okay. By definition, it is phi n of x is a polynomial of order n.
X to the power n.
Not x to the power n, polynomial of the order n. So phi n of x will be something like a n x power n plus a n minus 1 x power n minus 1 plus etc. a0. By definition, it is this.
Sir, this is for only hypergeometric differential equations. Like for we can assume phi n to be of this type only for hypergeometric differential equations or in general.
Okay, so initially I started saying that there are phi n of x, okay, which is basically equal to bra x phi n. This get phi n form a basis. When you look at in this aspect, there is no differential equation, nothing. Okay, there is some set of vectors phi n, its position representation is phi n of x. It is having some orthogonality relation like this. So here now I am saying that this phi n of x are polynomials of order n. That is by definition I am taking it. Okay. If I by definition I am taking it, okay. Now with rho of x, non-rho of x and the interval a b, without the idea of the geometrical hypergeometric differential equation, Rodrigues function, this generating function, don't worry about any of those things. We are not even thinking on those lines. I have phi n of x, which are polynomial of the order n, which is having this orthogonality relation. I can find out phi 0, phi 1, phi 2, etc. all those polynomials without bringing in the hypergeometric differential equation, without bringing the Rodrigues formula, without bringing in the which one, the generating function.
Okay.
Okay. Now,
Yes.
next interesting thing is, see, whoever wants to leave, they can leave. I am just discussing things. Okay. So next question is, if I find, suppose I found some phi n of x using this. Okay. Can this phi n of x is a solution to a differential equation? You can ask that question. I got from this orthogonality relation some polynomials. Is that polynomial is a solution for a hypergeometric differential equation? You can ask that question. If I had to ask that question, so what I should do? I had to find out a differential equation which is actually satisfy those criteria. Okay. See whether you can actually get a differential equation which actually give you the same solution. It is possible. Okay. It is possible. So you have to find out that differential equation. So one way is I found phi n of x, I have this orthogonal relation, I got all phi n of x. Whether this is some solution to some differential equation, yes, it is possible for you to find out a hypergeometric differential equation. That hypergeometric differential equation solutions are this. It is possible because you can write down any differential equation actually and get this polynomial solution, because hypergeometric differential equations coefficient satisfies certain condition, then suppose coefficient satisfies certain conditions, you can actually find out the orthogonal polynomials as a solution. So I got a certain orthogonal polynomials. So let me find out what is the sigma x and rho tau of x and lambda which can give you that solution. It is possible. Okay. So these two are different aspects, but you can actually connect one to another one. But I don't need a knowledge of the other one to get this. Or I don't have, see, suppose I don't know anything about the orthogonality relation, the polynomials, the base is nothing. I have only the differential equation, I have only the sigma of x, tau of x and lambda. If that satisfies that conditions, I can find a phi n of x. Now I don't even have this Rodrigues formula, and I don't even have the differential equation. I only have the generating function. From the generating function I can calculate set of polynomials, the phi n of x, which are all orthogonal. So each of them can exist as an independent identity, independent formalism, but you can connect one to another one. Okay, is that clear?
Yes, sir. Yes,
Yeah.
sir. Thank you, sir.
Yeah.
Sir,
Yeah.
sir, one more point. Sir, this rho of x, how we fix, sir?
Okay, so rho of,
This wave function.
so weight function, you can say tomorrow or today after the class you can go and think about some rho of x, okay, and some interval a and b, and you can start deriving some polynomials in your name. Okay. Only problem is whether somebody else should not have been done that so far. So you can take any rho of x and the interval you wish. Okay.
Some choice.
This is your choice. But as a physicist, okay, there should be some meaning to that. When now I am doing some problem, but that problem, my rho of x will be fixed to something. I will not have a freedom to fix that. Okay, but I can take any rho of x and interval a b and try to generate my own set of polynomials. Okay, that is my freedom. But certain physics problem, that rho of x. So if you look at the harmonic oscillator, quantum mechanical harmonic oscillator problem, this rho of x will be e power minus x square.
So we are more interested in which the main function which are having a square integrability, which brings square integrability.
Okay, so that obviously now if you are looking at the phi n of x into rho of x, which is a square integral function. So if you are looking at the quantum mechanics, obviously you should have to worry about. See, that's what you look at these conditions I have written, rho of x into sigma of x, okay, which at x is equal to a and x is equal to b goes to 0. This will fix, okay, this will give you some some indication towards the square integrability, okay. So the physics problem is different. Mathematically you can derive any kind of polynomials which actually not even a square integral wave functions, square integral functions, okay. So but physics, when you look at, you may be interested with a certain set of functions which are square integrable, because quantum mechanics happens in the square integral space, okay. Even so many physics.
Classical orthogonal polynomial means that it's a sort of square integral.
See, you look at this, when I those classical orthogonal polynomials actually satisfies this condition, okay, and satisfy this condition, and this is basically an. This an is numbers, okay, they are not infinity. Suppose this is infinity, then it is not square integrable. So we have to give an an which is not infinite, okay, because this is basically give you the square integrability, right? When n is equal to m, it is a square integrability condition, okay. So if this is finite, if the right hand side is finite for n is equal to m, it implies that it is square integrable, okay. So
Okay.
any other question?